Okay, let's start. This video is very important to have it done well. It's well fitted. What is this video about? This video is about yes, the Biparite command and control system. So the board is here from coding software. So I'm gonna be working on the board, but I'm gonna be working on paper too. So, we've been working on both axes of the model here, but let me see my face. Yep, I can see the board. Yes, so I can see the board. Half on the board, half on the paper. Can the board be seen? Yeah. You see the board? Yes, you can see the board. Yes, you can see the board. Yeah, you can find the title now. So we need to go chalk or the title. So this means I write the title here. Okay, so it's a bipolar, bypass the parity command. Command sequences. So, so I'm going to go around the definition of the system I'm doing, or really what I'm really going to work on. Let's just start doing it properly. The bipolar. So, okay. So you have, so bipolar means you have two sides. It's going to be alive, you cannot be enter, or exit. This will be two instructions you have. So the command bipolar is two. But my enter is your exit. So but it's not vice versa. We share an exit. Enter or exit. Think of it as commands. Enter or exit. Again, open or close. Open the file or close the file. But I'm going to give you an instruction to this system because one command that does two things. It's basically doesn't need to reduce something because one is implemented in the system. So it's bipolar. It's 2 1. It's 2 in 1. 2 in 1 command. 2 in 1 command. So 2 in 1. So enter, exit, open and close. We're going to use this example. But I'm going to show you probably how to do it. So you got bipolar. Definition of bipolar. So essentially, bipolar is order or chaos. Bipolar can be order or chaos. It's an error system. So either it's order or chaos. You have those two bipolar. Eat or don't eat. You said live or die, alive or dead. You have the bypass, like a bypass means like a graph of graphs of bipolar systems. So you have a DAG, a graph like open, close, enter, start, stop. So I'm going to try to do a graph example, but I'm going to try to use probably so you get. I'm going to use it probably good. Start, I'm going to make it an active station. So I'm really good at model mine anyway. So you got a DFA, which is this fact automaton. We have the non-equivalent of the DFA. So you have an NDFA, i.e. DFA. So, I'm going to start to give you an example of the system more formally. So, I will use this kind of way to have a system of I love tennis. So, tennis is stainless chain. Should I use football or should I use chess? Oh yes, three-player chess. Let's use chess. No, three-player chess. Or tennis, because chess is two dynamics to this. Well, we can model chess. Tennis. So tennis basically has scores from 0. So it goes from 0 to set of to 2. So you're gonna play 2 games of tennis, which is 1 set. I believe 2 games is 1 set. You have 0, 0, 0, 15, 13, 45, and then max point. You get 3 games in tennis, 3 games. So you get 1 point. So we're gonna play 3 games, 2 games here. So if you have two opponents, opponent A and B, you have a code score of score tally of 0-0-0-0 until they reach that 2 points, 2 games, 2 different realities. So the kind of a non-distribution function automaton, which includes a DFA that is bipartite. So it just means you can have two digital models of it. So you're gonna have state machine, start, stop, open, close, enter or exit. Enter, start, enter, exit. So basically, open and close. So this can give you a resume state. But basically, the start state is basically machine start. So you got the standard start state of a machine, which is the arrow. An arrow has circle. This is the enter state. So enter or enter start. So this is start. So you start from here, and you have a game. Let's say a game of I'm busy. I'm streaming. No, don't talk to me. I'm working, mate. You can't help me do this, mate. I'm working. I'm sorry, mate. I can't help you. I'm busy myself, mate. I told you this before. I'm sorry. Can't help you, mate. Sorry about this. Sorry about this, mate. So you have this model here. So say player A or Alice player A, bought play 2 games and Alice wins. So I'm getting some scores up now. They start at 0-0, and Alice gets in the first game, Alice gets 15 0, 30 30 0, 30 15, 45 30 1 1 1 0 1 0. And basically, these 2 games have a read like start. So this is the Alice ball game 1. Game 1. So Alice wins by 45 and then 1.0. So 1.0. So Alice point is 15. Ball's point is 0. Alice point is 30. Ball point is 0. Alice point is 40, 45. Ball point is 0. When Alice is 15, Bob is 0. When Alice is 30, Bob is 0. When Alice is 40, Bob point is 15. When Alice is 45, Bob's point is when Alice is 30. When Alice is 45. When Alice is 45, 45, ball point is 30. When Alice is 45, ball point is 0. It's 30. So Alice wins 1 game. 1 game to Alice. So the basically the sequence instructions are isomorphic to it, but this division table is pivotal. So we have to have a switch of state. So the first game is won by Alice. So how this works is you have start, which is so when you exit the game, you have to restart it. Restart. But you have when the game starts, you have everyone 0-0. So Alice the ball has 2 machines. So Alice game goes like 15, and then 15, and then this is 15, 30, 45. So 15, 30, 45, 1. And this Alice side. And Bob games goes 0-0, 15, 30, 0. So we have to send one to reach. So Alice starts. So basically they all start as start. So 15 0 0 is starts. Start. What's it done? But so the Biparite solution is start. So this is order start. You didn't want to start order start. Like it's like an order start, but in the real world. So you get the order start and you get this order start, which means this order starts. You have a chaos start and a chaos stop. Chaos stop and this no chaos stop. So basically, the no chaos stop and chaos stop are two based on the rule entropy of the system. So you have to work one with the other. So you go to the actual data, like actual transition. So transition needs to happen via consequences. So this is social concern, superior to so when Bob has when the machine changes for Alice has a enter code enter. Alice enter. Alice enter. Alice enter. Alice enter. So Alice enters 3 times. So 3E. So the encoding will be 3 enters. 3E. 3E for Alice. To Alice. For Alice. So for Alice. 3E Alice equals Alice. Alice. So far 3 E's. And then oh no. Yes. So enter. So enter. Enter. Not enter. So yeah, so 3 E's enter, and then Bob gets a point. That basically 2 normal. 1, 2. So 2 enters, 2E, 2E. So 2 enters means the highlight gets 2 points. And that is 15, 30, and then 15, 30, and 15, 30, and 45, 40. 15, 30, 40, then 45. So Ali gets 3 points, 15, 30, and 40. What is 3 is 3 encodings of 3 points. 15, 30, and 45. 3 to the 40. 15, 30, 15, 30, and 30. Sorry, 15, 30, and so this is 2 enters, not 3. 15, 30, and 30. And then you get 45. You get 45, so 15, and then what becomes, so you get 3, and Alice basically 3 enters of points, and 1 exit. But because there's no to check, there's no point taking away from Alice. So you get the exit opposite. So you get 15. 15. So from there on, you have 15, 30, 15, 30. Which is 40, 40, 45, 45. So Bob gets 2 enters. 3, so you get 2 enters to 2 enters, which means that they both have the same measure of points, but not the same points. So the sequence is basically Alice has 2 E's, 2 E's, 2 E's for every 2 E's, and then 2 E's followed by Bob's 2 E's, 2 enters of points. So A 2 E, Alice comma B 2 E. So Bob is now at 40, 30. He's doing 30, 30. No, Bob is now at 15. 30, 30. No, Bob has 3 E's after Alice. No, wait, 2 E's, so you get 40, 15. 15, you get 30, 15. 1, 2. No, it's 2 E to 2 E. And then Bob, and then 45. So, and then Alice gets 1 more E. So that would be 2, Alice 2 E, and then Alice E. Alice 1 E. 1 enter. So Alice now includes 45, 2 E, so it's 2 E. So Alice point goes from 2 E 2E or 2 enters of points. Bob goes 2 enters of points, and Bob, and then Alice gets 3E. So Alice is here. Alice gets 3E. Or this one, try that. 0, 1, 2, 3, 4. Alice gets 2E, 2E. So the number obviously, because it's 10 there, so Alice gets 3E because it's get 40. So Alice gets 3E to get into one match point. One point. One full point to Alice. So basically, because you get 40 in there, so so because you got number 40 in that. So Alice gets 15, 30, 40, 45, 15, 30, 40, and then Bob gets 15, 30, and doesn't get 45, so Alice gets 45, and then Bob gets 45, 40, 45, 50. So, but Alice never beats Bob. Bob only beats Alice one game, the first game. So that's how that works. So mathematically, it makes sense for the system. Basically, let me just show you on the board. So the spots you got here. Oh, can you see guys? Enter, exit. So you get enter, you get exit. Open, you have close. And start, you have stop. And basically this is the machine model for Biparite system. So when Alice has two entries of start, Alice has Bob has 0. So 2E to make up the 15, 30, 40, going to 40, 45, 1, 2, 3, 4, 5. To get 5 points before you get to 1. So you have the encoding sequence. So the sequence of instruction sets have 2E, then Bob has 3E, and then then Alice gets the final 3 encoding, 3 enters of scores. So the enters written in the state of the program via the Nexus Link system, which basically I get to open and close the file and start or stop. So the game now stops. And this is a hold state stops. But if when it stops and it's finished, this state basically is finished, you get a reset of the state, so you get a restart. And then the other ones get a pop. So say the same thing happens, but opposite. So now Bob gets the same point of Alice. Basically, now Bob gets the same sequence and the same sequence which alternate sequence between Bob and Alice. You now have to understand. Sorry guys about that. So you now have to understand that it's a one-to-one mapping of bipartite rules. So they can be either order or chaos, or chaos or order. Disorder or chaos. Disorder, chaos or order or chaos, or disorder or order, chaos and disorder or disorder. So basically that's how the system works. Mathematically, this can be framed as like this can work like this. So this will work like this. So I'm gonna write it down here. So you have a sender and a receiver, but you have a sender on the left. So you have read. If you can read, you can write. Because if you have a read-write tree, RWX, read-write execute tree, and you have R equals right shift 0, R equals W equals R, right shift 2. And you have F equals R, right shift 4. Right shift 4. This is basically how this works in practice in computer science. So you can have this model computable too, and other models, but R is right shift 1. So R is actually 1. Read. So the R stands for read, R stands for read, W stands for write, and X stands for execute. So basically, you're trying to encode this into an execution system. If it's read and write, these are operations you can perform. If you can perform read, you can perform write. So it's a bipartite system. So you can perform read, you can perform a write. So it's basically to order. And how you do this mathematically on the calculator is like this. Take three binary numbers. Let's take 8 bits. 8 bits, and you have a flag for read, write, execute. So this is basically a flag, the flag. So the flag, so if you have a flag, which is an operation you can perform a flag, the flag is already encoded in the system. So this could be like a regular expression flags of RWX, which I can give you an example now. So you have a regular expression, a stream of information in binary, and you have a flag RWF. So you enable read, you enable write, and you enable execution in this kind of regular special model of the system. But you can have this as a regular special model, or you can have this as a standard read, write, execution. But you can have this another way. The other way I want to show you is basically a disjoint system. Is basically a disjoint. You can have this as a pipe object, which is the best way to do it. So how this works? The way I saw it is basically RWX pipe. So the pipe operator being on the, so you get RWX, which is a vector. So you get a vector here of RWX. 1 second, guys. It's kind of like dark. So just kind of right with 2 lights to understand. So you have a read RWX, which means read, write, execute. But these are all encodings. So you have write, meaning read, reading, write, two left shift, two right shift. So you get R right shift 2. So if R is the number 1 right shift, if you get 001 being the encoding of read, R equals 001, which means you have the number 1 in binary. The right shift, wait. No. Basically, you meant to do right shift. So basically, the right shift, no, basically the left shift. So we're gonna use not the left shift, not the right shift, the left shift. So this will be left shift 2, left shift 1, left shift 2. So the left shift will be 2. That will be so R read of R equals 0 1 will become left shift, which will become 1 1 0. 1 0 0. And this is so R now is 1 0, and then R will be R, and then right of a read will be when R is 1 0 0. This will become 1. Because you have to switch it 2, so you now get 1 0 0. So 1 0 0 will now become 1 0 0 1 0 0 0. So 1 2 3 4 5 6. So you have R become the literal number or hexadecimal number of 0 1 1. 0 1 1. So 0 1 1 will become 1. So in binary, let me get my calculator. In binary you get 1 0 0. And 1 0 0 will become so you have 0 0 1, and you have right shift of 0 0 1. 0 0 1, 0 0 1, 0 0 1, 0 0 1, right shift 1. You get or left shift 1. Oh, it's left shift 2. So you get 0 0 0 0 1. Oh, so you get 0 1. 0 0 0 1, left shift 2 become left shift 2 become. Oh, okay, I see. Left shift 1, not 2. So you have 0 0 1, left shift 0 1 1. Okay. 0 0 1. Okay, so you get a number. That's a number 1. Left shift 1. Left shift. That's a number of 2. You get 4. So this will be 4. So number of 1 becomes 4. and then you now have number 4 for right. So right will become 4. Now basically this right has now flipped. So you have now realigned the poles. So now you now have the opposite. So you're now writing. So now you're writing. You have to start from this pole. So this is a new start. So this pole represents right operations, and this would be so this type of operation is like so if you're reading, you're consuming. If you're writing, you're sending. So you have to have a different notation. So if I do if I have RXW pipe, and I put a greater than sign, a greater than sign, a greater than or equal to sign. Here, you are reading, you're writing, you're reading. So I'm putting a greater than sign on the right side. This means I'm writing to something. But if I put it on the so if I put a pipe operator and a greater sign, that's I'm writing, so it's a right operation. So if I'm writing, so if I write pipe write pipe right, I am writing. So this basically, if I start, so the matrix is a read, write, execute. But if I have write, just write pipe greater sign, I'm just writing. If I have read, then a write, then I'm reading and writing. So it's a read R for read, W for write on the bottom, and X for execute for execution. So let's use this table set first. So you have 4 now. So write equals to 4. So read equals number 4 when it's encoded as executable instruction. So this number 4 has a weight, and that weight is the weight of a graph. This can be just a the weight of a read operation or to some kind of arbitrary function. This is a function functor. There. So you get read, write, and execute. So you get read, write. So read equals to R001 equals 100, and now write 100, R100, 100. R100, R4, decimal 4. So the decimal number is 4, R4. So 1 becomes 4. So 4 will be, let's say 4 is R shifted 2. R will be 1. But 1 will be 1. So 1 shifted 4 times. Left shifted 4 times will give you 16. So right equals 16. So this is hexadecimal encoding. So you have 16 bits of data now. 16 bits of data in an 8 encoding table. In an 8 encoding table, you can use. Can you come in here and busy, man? Stop disturbing me. But you're coming here like you need something. Sorry about that. You have a read. So if you have R1, so if you have one, or left shift, one left shift, 4, you're now talking about execution. So one left shift 4. So you're now thinking about oh no, so sorry. No, sorry. So basically, you right. So that right. So you have to have the right. So if the read is right, so we have 16, and 16 will be 16 bits of data. So 16 will basically, because right 4 equals 16 encoding table, 16 are bits of data. 16 left shift 4, left shift 1, 2, and 3. Okay, left shift, let's use 1, 2, and 3. 16 shift left shift 3, not 4, will be 128. So you have the encoder table for R equals 4, 16, and 128 bits of data. So basically, you can now have this mapping properly. So 4 bits of data is good enough for a system to encode some information, and you get the polar opposite. So the polar opposite will be if you can. open a file. For example, if you can, so basically, what we've done here is encoding the system. So so you need 4 bits of data, 4 segments of space in bits, to have a pipe and a read. Read. So this is read pipe, write, greater sign. And you have write pipe, greater than sign, greater than, and you have execute pipe greater than. So this represents encoding tables of sparse structure. But the encoding tables are little things that can run the code. So if you have a Cisco bottom-up model and you had read, write, execute, you can have R or read, you can write, if you write, you can execute. But this is disjoint. There's no relationship. There's only one relationship between read, write, and execute. But there's no, you can't, so you have only one relationship. So read is the standard relationship. Everything related to read is operational system. So this one is just a read. If you read, you can write and you can execute. Read, you can write. And if you can write, you can execute. But they point one way. They're forward. So that's what I'm about. If you can read, you can execute. But if you want to point one way or the other, you can have read to write to execute. So read is at the root node. On the right, and then it points to write, and write is basically one node, and then you have execute, which is basically one node extra, but it's basically read, write, and execute permission tree. So left node is root, read, right node, left node is root node. Right node is write and left node is execute. So if you want to execute data, you have to look in the 180-bit segment. It's 180-bit segment. So these are all segmented because those separated. So this pointer points to 3 things, but it's segmented. So you have to look in the right place to execute commission. So you can, for example, if I'm for the tennis scores, we had the first game. Which was execution. So you have 3E. You have 3E. You have 15, 30, 40. 15, 30. Oh, we have 15, 2, 1, 2, 3. So you have 2 enters of point to Alice. So Alice's executable will be write 2E, write 2E, write 2 encodings of Alice entering as point. So Alice is now at 15, 30, 40. So 15, 30, and 40. So write 3 enter of a phone. So Andy is a 15, 30, 40. That means Bob is at 0, 0, 0, 0, 0. And then Bob gets 15. Bob gets 15. So as then Bob gets 30. Then Bob gets 40. 40. 40. Then Ali gets 45 and 1. And gets 1. So basically, write 3E, and then Bob will write his enter. So it'll be 15, 30, and 40. So Bob writes his own point. Bob writes 2E, 15, 30. So Bob writes 2E, 15, 30, 40. 15, 30. So Bob writes 2E, write to Bob's address. 2E, so encoding. So that will become 1, 2, 3, 15, 30, 45. So when Alice writes 3 enters or 3E, Bob enters the code. Bob is writing to a system on the fly. So 30, 15, 30, 40, and this 40 will be Alice's point of 40. So Alice is basically point 40 now. So 40. So Bob now continues at 15. Bob 15, 30, 45. So 15, 30, 40. 40. So when Bob is at 40, Bob is at 40. Bob has 15, 30, 40. Bob has 3 enters. So Alice now needs 2 more points to get to Bob. So Alice, I'm almost done.
Nice.
Oh, sorry about that. So Alice now needs to have 3. So write 2. So Alice now write 2E, and that will be 40 and 45. 45, this is just like 45 and 1. So Alice gets 1 point, 1 point, 1 point. So you know the 1 point is Alice's 1 to Bob's 40, 40, no, 1 match point to Alice. So this match point to Alice is distant. So this is how this works. So the digital is basically, you can't see this, guys. But you see, I'm just going to close window for you to see, guys. But you know, this right thing is the solution of concern. So you can see it here. So the full thing is here. Here. So the full thing, as you can see, we started from read, write, and execute, but we separated operations from operators. So basically, it's a sparse model for for separating these kind of things. But it works because it's like can't see, guys. Nothing picture. So this is get right of 3e to Alice. Now, this is the Alice address space, which contains 8, 4, 16, and 128. 4, 16, and 128 here. And basically, because of read, write, execute, and you have read, write, execute in that sequence. This is a sequence because the series model, which is in parallel, but it's distant. So you have this tree model here. But it works. So you get Bob's Alice. So write Alice gets so Alice writes 3 so the series will be Alice writes 3e, Bob writes 3e, Alice writes 2e, and Alice is with 1 point. And then 1 match point, and that's how that solution works. So this is the bipolar order. So the order and chaos is the ratio of the system. So order means like we got what we wanted, we got the order, but what we wanted basically make sure the ratio between 0 and 1. So if Alice is ordered, for example, because Alice 1, she has order, but the ratio of order to Bob's this order is basically 1 match 1 seek 1 2 2 wins. 2 rights, 2 rights to. So basically, you have a total. The total, so basically 1, 2, 3. 1, 2, 3. So you have a total of 5 points. So you have the total. So this is a sequences. It's all of the sequences divided by the total series. And that would be all of Alice sequences. Sequences would be 3 plus 3. That's 6 enters. In total, no, 5 enters in total. Rise of a RAM over 5 enters for Alice, 5 enters of score points over Alice over minus range minus the total number. Okay, so basically the total number will be how many enters? 1, 2, 3. 5 enters. You get 5 enters. You get 6, 7, 8. 8 minus 5 is 4. 8 minus 5 is 8, 5, 6, 7, 8 is 3. So it's 3 divided by 8. So the order will be 3 divided by the total number of gains, which is 1. The total number of points, which is 1, 2, 3, 4, which is 10. So 3 divided by 10 is a low order. So basically 3 divided by 10 because it's 10 3 divided by 1, 2, 3, 4. 3 divided by 1, 2, 3, 4, 5, 6, 7. 3 divided by 7, 7, because there's 7 games. 2 divided by 7 is the total of the system. So 2 divided by 7 will be total order of the system. So that'll be we've done 6 games. 6 games divided by 7 matches. 3 divided by 7. The measurement of order, or this order will be so 3 divided by 7 is the ratio of order. So this is basically Bob's basically 3 divided by 7 is 3 divided by 7 is 3 divided by 7. No. 3 normal calculator standard. 3 divided by 7 is 0.28 0.4285 or 0.429. So basically, Alice has a great or bad order. So in the next game, 0.4 so we need 3 divided by 3 divided by 7. So this is basically chaos already. Just look at it. It's not halfway, but the ratio actually is congruent to 0.429. And this means that there's an order ratio. The order is Alice is placing disorder in a game. But basically, it's a dimensional game theory model I invented to adapt. So basically 0.439 represents it's not 0.5, it's not even halfway between order and chaos. And this kind of whatever Alice is doing has failing her to give her Alice is suffering in the framework of openness. So she's playing a hard game, a hard life. Thank you guys for watching the video. Like, share, subscribe if you want to. Like, share, subscribe. This is my YouTube channel, my journal. I'm still on the board, but I don't want any money. Just get me out of here if you guys can get me out of here. Thank you for watching this video.